smo nazaj. Mogoče še ena stvar sem jo pozabil prej omeniti. Predavanje bo potekalo v angleškem jeziku. Tako da, hi Matija.
Hello, good morning. Good morning everyone. Hi.
Good morning. So, in which country are you staying right now?
Right now I'm staying in Italy. I'm based in Rome, in Rome City.
Okay.
Good morning.
So, so we are streaming from Italy directly. So, Mattia, you will be talking about the 5G automation inside of 5G networks, slicing, what slicing is, and everything that is hot in this topic right now.
Yes, yes, absolutely sure. I must say that 20 minutes is very small slot. There is for sure all the chance you want to go deeper because 5G is a tremendous topic in these days in Europe, not only but worldwide, I would say. And 5G has a lot of impact. Not on the technology only. It's not something that gives only more speed. That's not the type for 5G. It can potentially change really the way people do the daily life, potentially with the technology. And as you said, I will cover quickly, but that there will be for sure space for questions and in the future a lot of more detailed session for anyone who needs it to explain better how the technology is developed for this new network.
Okay.
So can I start?
Yeah, please start. The stage is yours, Mattia.
Okay, thank you. Morning, everyone. My name is Mattia. As written and as introduced, I'm responsible for inside Nokia for the ION products, which is basically related to the connectivity, IP connectivity. And we cover also, as of today, the packet core for the 4G, 5G solutions that Nokia has. It's and especially now in the 5G, it is really a hot topic in these days. Time is very short, I must say. So I will proceed to the next slides, which introduce the concept of 5G. With such a short time, there is one key message that for me is really important for you to remember, to bring out from this session. The difference from 4G to 5G, sorry, from 3G to 4G was mainly the fact of capacity. As you remember, the past networks, 2G, 3G, and 4G, saw a very big increase in the capacity. Nowadays, we have on our single smartphone bandwidth enough to do video streaming, multimedia, GPS navigator, things about Waze, Google Maps, to do internet online shops, to do video calls, all those applications. They just need a bit more capacity. 3G was very limited. You may remember when with 3G people started to send the TV over the mobile, and it was impossible because it was very low bandwidth and the quality was not good. I remember when there was the World Cup in 2006, the World Cup was first sent also to mobile, but the mobile had a very small screen, and seeing a game there, it was just nonsense. Then with 4G, they had more bandwidth, and 4G arrived in 2018 approximately. So from 2018 to 2020, we just experienced more bandwidth and a lot more of application only because of this. Now, the important thing I would like you to remember is 5G is not only more bandwidth again, because for the typical use case from a mobile phone, from a smartphone, the bandwidth you already have to do many things is already good, okay? The actual 4G bandwidth. 5G is not at all only providing extra bandwidth, arriving to more than 10 gigabit, but it is also covering two critical aspects to change the way people work and live their lives. It impacts the latency and the connectivity. What I mean by connectivity? Connectivity, I mean the density of the user. In short, 5G will be able to enclose the world that we nowadays call the IoT. Now, in IoT, you have in a small area, think about a big port, a big city, for example, sorry, a big factory, for example, in which there are a lot of sensor, actuators, machine precision application, in which in a 1 kilometer square area, you may have 10,000 different sensors, temperature, pressure, etc. This is the IoT world. Now, in such a densified area, the 5G has been designed to guarantee the capacity and the latency for such also concentrated environments. And the second part, really, really important, is the latency. Our today's network limit is not anymore the capacity, it is the latency. Typical networks nowadays have 100 milliseconds latency, for example. To bring the applications that we want with 5G, we need to reduce the latency. But reducing latency is not as easy as increasing capacity, because the latency limit is a physical limit, the speed of light. We all know that the speed of light is fixed. No company, no engineer, no one can change the speed of light or increase it or make it slower. It's just impossible. This is physics. So the only thing we can do is get the things closer to each other to reduce the latency. For this reason, 5G was built in mind in the future to support those big new use cases, massive to machine type communication. Here is one of the cases, one of the use cases mentioned below, in which, for example, we have a high density of, like a port here. This is the port of Hamburg in Germany. It's one of the best use cases for 5G, in which you have an incredible amount of sensors, and not only sensors, I would say also other devices, smaller devices, of IoT devices in a small area, all concentrated. You may have enhanced mobile broadband customer experience applications, in which, in this case, differently than the previous use case, you have less density, but you need high experiences. Think about a football game in a stadium, in which the people who attend the stadium can see not only the game in reality, but can experiment some augmented reality on their devices. Augmented reality needs quite a lot of bandwidth. So the enhanced mobile broadband is a type of traffic that needs has less densification, but probably needs a higher bandwidth in this case, or the ultra reliable low latency communication. This is fantastic use case for 5G. It will be about self-remote driving, connected cars. If in the future you will be able to have the 5G inside the car could control each other to avoid accidents, to optimize the flux of the cars on a street, to make it faster so that there is less traffic. To do this in this kind of application, you don't need high bandwidth, and you do not need 1,000 of users, sorry, 100,000 of users per kilometer square. You need very, very low latency, because a car that travels at 100 kilometers an hour, in 1 second, it makes 36 meters, okay? So you need really, really low latency. And in these use cases, we saw a case in which you have a very, very high densification of sensors, a use case with high bandwidth, and some cases with very, very low latency. Well, nowadays, 4G can barely satisfy this one only, okay? The 5G will satisfy the MMTC, eMBB, and URLLC type of communication. How we can do this? Well, the whole presentation will be focusing on two sections here, two technical parts, the IP anyhole and the cloud interconnect. Remember that we said, 5 seconds ago, I just said, how can the 5G achieve this? Well, it changed the radio architecture, okay? This is the first thing, how. To reduce latency, this is important, we have to bring the resources, the computing resources near the user, because otherwise the latency becomes too high and we cannot tolerate. We have applications that needs latency with less than 1 millisecond. So how do we achieve this? The first thing is the new radio architecture. The new radio architecture is here. The 5G Node B, following up from the previous 4G Node B, is decoupled in 3 different components. You have the RU, the DU, and the CU. Now, some of these components here will have onboard some computing resources, so that the resources, the computation analysis, will not be done in the center, in the data center, in the cloud, centralized, that has 100 milliseconds of latency. Will be done directly here. And this is the famous concept that we all hear in these days called edge cloud. When someone mentions edge cloud, think about it really means having the computing resources as close as possible to the user, ideally to the antenna, okay? Now the antenna, sorry, not the antenna, to the BTS, I would say, to the G Node B, it's called in 5G terms. Now, when you go decouple the G Node B into 3 different parts, the antenna, the radio unit, the data unit, the centralized unit, and you can separate, you obtain 3 different levels of access. Well, let's say 2 different levels, the front hauling, the mid hauling, and then the typical, of course, back hauling. And this is a very important slide that can explain which are the architectural options for the access, for the radio access network in 5G, and to support it. So you may have the solution in which you need a distributed computing approach, in which the computing must be brought into the BTS. In this case, we have computing resources here. We can support really, really fast and low latency applications. There are certain applications in which the computing resources can be removed, and this is where, well, removed and brought to the mobile core, to the typical data center. And this is when it opens for the 3 sections of front hauling, mid hauling, and back hauling here. Depending on the type of applications that you have, you can adopt as RAN architectures those different solutions. The ports will change. You will encounter CPRI ports or enhanced CPRI ports. From Nokia point of view, I cannot stress the fact that in 5G, when you have really, really precision and low latency mechanism, synchronization is really important. You need to have a reliable mechanism for synchronization, given by both the contemporary use of synchronous Ethernet and PTP-V2 together to achieve a very precise phase and frequency synchronization. Especially when you start to have front hauling in there, and you need a very synchronized clock across the radio, the DU, and the CU there. The bandwidth increases. Typically, we can have 10 gigabit in front hauling, back hauling in 5G with the higher bandwidth would be basically on 100 gigabit ports typically. So this is just a section on to close the first section of this presentation to very quickly identify which is the impact in the network of the 5G. What is the reason? The second, well, to finish with the first one, we as Nokia have built those devices. It's the 7250. Those are the devices that we use typically to cover for these 3 cases: front hauling, mid hauling, and back hauling. This is the product family that we use to support those 3 different architectures. Okay, then there is a whole bunch of discussion we can open on this, which one is better, etc. It depends on a combination of many factors. The second thing I want to cover, and it was also mentioned by our colleagues during the introduction, is about slicing. Everyone knows that 5G is about slicing, okay? But what does it really mean, slicing? Well, slicing in 5G means to bring a slice of the service guaranteed not to the antenna or to the switch, but if in 5G it means to bring a slice directly to the client. It can be a sensor or it can be a smartphone. By definition, the 5G standards guarantees up to 8 different slices approximately for each client. Each of these can be served by a different application. So if you have a sensor talking to application or a smartphone talking, doing 2-3 things at a time in parallel, video, internet browsing, and streaming TV, he will get 3 different slices serving to it. And those slices are not single section, they are end-to-end slices that cover everything from the mobile to the core, okay? So you will have, for example, a first section of a slice from your mobile to the antenna. Then there will be another section from the antenna to the edge, and then from the edge to the core, and then from the core to the mobile packet core in which the session of the client is terminated. Who orchestrates this network slicing? There is an orchestrator on top, and we as Nokia provide an end-to-end solution because we have the orchestrators end-to-end, and we also have the single controller, which are controlled by the orchestrator for the different section. So for instance, when I will skip here, for example, for instance, when you create a network slice, an end-to-end network slice, the orchestrator creates it and it gives a unique identifier. For example, here is this one. The orchestrator then puts down this new slice dynamically to the different controllers, and it makes sure that there is a slice opened here, a radio slice opened here from the user device to the antenna, and then this is more detailed for the transport part. You will have a network slice, for example, from the radio unit to the DU. This will be a slice. You see, which slice are used? This depends on the SLA. So if there is an application here that needs better latency, but a smaller throughput, it will be assigned to a certain SLA and assigned a given network slice across the one available. Same thing will happen from the DU to the CU we saw before, and then other slices can get from the CU to the central core part. Of course, there will be then a final slice to dedicate the service in the mobile packet core. Here we have the EPC, basically. The EPC will have also a slice for it. The unit that orchestrates dynamically this end-to-end slices creation is the orchestrator, okay? So for the networking, this is how it happens. You have the orchestrator on top. Using the API, it goes to the transport slice orchestrator. The transport slice orchestrator, it checks the resources, of course, and then using it can be anything, EVPNs, segment routing, anything. It creates dynamically those slices and paths and tunnels from those units, from the front haul, the mid haul, and the back haul, and then it joins at the end those slices with the run slice and the access, and the run slice to the mobile packet core. Okay, Nokia is able to achieve this end-to-end completely alone in a 5G network. Okay, this is really important. It is really important because this is the end-to-end capability to invest in the technology in such a way that you can achieve the previously mentioned use cases. Okay, remember we had the mobile ultra low latency and the massive to machine type communication. Those type of applications, when needed to be brought on IP, they need this kind of solution, this kind of architecture, we as Nokia are able to achieve this in the providing, as you saw, both not only the transport that you saw with the router, but also with the orchestration part, the so-called SDN. In this section for transport, this is evidently an SDN application, a software-defined networking application that comes from the main end-to-end orchestrator. So to recap, I hope that I stayed on time. I don't know how much time I left. 20 minutes were very small type of time. There is all chance to go on different sessions. The main important messages that I would like to give is we as Nokia have technological capabilities to achieve an end-to-end solution, 5G solution, to support the new applications that 5G will bring, and we truly hope that the world will recognize the 5G as a technology enabler for these new solutions. We as Nokia can do not only the radio part, can also achieve the transport part. So it is the so-called XOL, any transport. We have dedicated product line for it, and we also have the capability to fully achieve the slicing, all the slicing that are needed. As you can see, the end-to-end network slice is then sub-made of run slice, transport slice, and core slice in the mobile packet core. Those slices are end-to-end, meaning from the user, from the sensor, the smartphone, etc., all the way to the packet core, and they are dynamically joined together by the orchestration and SDN controllers. So I don't have any other messages here to give. I would like to use the remaining time, if there is some, for questions.